Okay, this is going to be our third video in our inductance series. In this video, we're going to be discussing magnetic field energy, and this is going to be the content from section 30.3 from the textbook. Okay, so we'll start off right away. And so we have our diagram that we looked at last time, where we have some sort of a variable source of EMF. We're driving some sort of a current through our inductor. And so establishing this current going through the inductor requires some input of energy. Okay, and as we're inputting energy, well, this energy is going to end up being stored, and it turns out that the energy is stored in the inductor, and it really turns out that the energy is stored in the magnetic field of the inductor. But we'll kind of get to that in a moment. We can kind of see how this works out here. As we start to drive a current through our inductor, we're causing an EMF between these two terminals, right? And so there's a potential difference between these two terminals, VAB, right? And so the source has to be transferring power to somewhere, and it turns out it's transferring it to our inductor, and the power that it's transferring has to be P is equal to VAB times our current I here. Okay, and again, remember we're using this lowercase I because this current is meant to be changing all the time. Okay. Strictly increasing in this case, I guess. So we want to now calculate the energy stored in the inductor. To calculate the energy stored in the inductor, we're gonna establish a final current I. So what we're going to do is we're going to go from 0 to I. Okay, and our inductor has an inductance of L. And as I said, an initial current of 0, and we're going to I. Okay, so we start off at 0, we go up to capital I current. If we assume that the inductor has negligible internal resistance, so none of our energy is being dissipated as heat, then it turns out that our power, which is equal to VAB times I, well, we saw that we can write our VAB in these terms, right? And so we end up with Li times the time rate of change of I. Okay. If we then remember that power can be written as the time rate of change of the work done, and we realize that all the work done here is done, and the energy supplied is stored in the inductor, well, then we can rewrite our power as du dt, so the time rate of change of the energy stored in the inductor, right? We can rearrange this to get du equals p dt, and so we have du, once we replace p for this expression here, because we have dt hitting dt, right, we end up with du is equal to Li di. Okay, and so this sort of begs for integration, right? We have two terms here that we can integrate. We integrate the left-hand side, we end up with u. You can kind of only barely see both of them on the screen here, but integrate the left-hand side, we end up with u. Integrate the right-hand side with respect to I, and we're going to integrate from 0 to capital I. This is from our 0 current all the way up to our maximum current of I. If we do that integration, we end up with the expression that we see here, 1/2 Li squared. This is the energy stored in an inductor. Okay, so that's our energy stored. This is the inductance of our inductor. And well, here's our integral. When we do the integral, we end up with the square of the final current over 2, right? Okay, so when the current reaches I, it's no longer increasing, right? That's the maximum current that we set, and so no more energy is being pumped into our inductor. And so what is this 1/2 Li squared really telling us? Well, it's telling us that is the energy stored as we go from 0 current, right, all the way up to our steady current of capital I. Okay, when we let's say we then turn off our source, we have this thing hooked up to some external circuit. At that point, our inductor is going to supply that much power back to the external circuit, or that much energy back to the external circuit, I should say. So this is potential energy. It's going to supply all of this potential energy back to the circuit, right? So as I mentioned above, the energy stored in this inductor is actually stored in the magnetic field, right? So we're going to take a look at the magnetic energy density of the magnetic field inside our inductor, okay? And we're going to look at we're going to develop it in a special case of a toroidal solenoid that we looked at before, but we're going to find that this really applies to sort of any magnetic field that we want to look at, okay? So let's start off here. The energy stored in the inductor is actually stored in the magnetic field, as I mentioned. This is actually really similar to the way that, if you guys remember back, I think it was chapter 24, that we looked at the energy stored in a parallel plate capacitor. We found there that the energy was stored in the electric field between the plates. This is very, very similar to the way that this inductor stores energy in its magnetic field. There is energy stored in the magnetic field itself. Okay, so we're going to try and develop an expression for this, and as I mentioned, we're going to be looking at a toroidal solenoid for this. We can assume that the magnetic field, so maybe, can I try to draw it here? Maybe I'll try to draw it. We can imagine, this is going to end up poorly, but we can imagine sort of a rectangular cross-section for our toroidal solenoid. You can imagine that it goes around all the way like this. It's kind of donut shaped, right? And if this is A, okay, so like a small cross section of the toroidal solenoid. And if you'd like a better picture, you can always look at the example we did in the last video. They have a nice image there that I think I included. So if this is A, and we assume that the magnetic field is uniform over this A, okay, and then we can sort of, let's call this R. Okay, so from the center of the toroid out to the sort of center of our donut here, but we're assuming that A is small and that the magnetic field is uniform inside the donut here. We can come up with the volume for our toroid if we kind of make this assumption that this is small. If we do that, then it's basically just going to end up being the area times the circumference of our toroid. So our volume is going to end up being 2 pi r A. Okay, and like I said in the last video, we just looked at what the self-inductance of our toroid is. That's why we had that image of the toroid there. We found that this is the self-inductance of the toroidal solenoid. Okay. I'm going to actually get rid of this image because it's very poorly drawn, and if anybody wants to see it, just take a look at the previous video. So using the expression that we just developed above here, doing this integral here, 30.9, if we then slip in the expression for the self-inductance, we end up with the expression that we see here. And if we're looking for the energy per unit volume, or our magnetic field energy density of the magnetic field in this toroid, well, we can just take the potential energy divided by the volume itself, which we just spoke about up here, right? That's our volume. And if we take this expression and divide it by the volume, we end up with the expression that we see here. Okay, so this is the energy per unit volume, or magnetic energy field density for our magnetic field in our toroidal solenoid. Okay. Now, we know that we can write the magnetic field of our toroidal solenoid in these terms here, which is also something we discussed last video, although I didn't do the calculation there. We spoke about the example from which it comes. But we can write this magnetic energy density here, this magnetic field energy density, in terms of the magnetic field. And if we do that, so I won't sort of go through any steps, but you can imagine just taking these variables and writing them in terms of B, right? We're just basically squaring a B, and we're going to have a leftover factor of a half here. And so if we do that, we can write the magnetic energy density in a vacuum as this expression that we have here. Okay, so this is another one that we're going to want to remember. And the reason we want to remember it is that even though we derived it in the special case of a toroidal solenoid, it turns out that this expression is going to be true for any magnetic field in a vacuum, right? And it would be true for magnetic fields not in a vacuum also if we just replaced mu naught for just mu, but we haven't talked about dielectrics, so we're not really going to go in that direction. We're just going to remember that this is the magnetic energy field density in a vacuum, and that this expression is general for any magnetic field in a vacuum. Okay. Okay, so we'll take a look at one example here before we move on. We're going to be looking at storing energy in an inductor. So let's read the example here. The electric power industry would like to find a way to efficiently store electric energy generated during low demand hours to help meet the need of customers' requirements during high demand hours. Could a large inductor be used? Okay, so we're going to find, we'll do the calculation. We're going to find that if you want to use inductors, you need a fairly large inductance. Inductors are used in this way in some power grids, but it's a fairly expensive and difficult way to store power for later use, right? So let's take a look at the example here. We want to know what inductance would be needed to store 1 kilowatt hour of energy in a coil carrying 200 amps, right? So our current is 200 amps. So what do we have? Well, we have the potential energy that we want to store, which is U. This is equal to, well, we're told that it's 1 kilowatt hour. Well, we kind of need this in joules, right? So what's 1 kilowatt hour in joules? Well, a kilowatt hour in joules is simply going to be, well, that's 10 to the 3 watts, right? A kilowatt, that's 10 to the 3 watts. So we have 10 to the 3 watts. And an hour, well, how many seconds is that? There's 60 seconds in a minute and 60 minutes in an hour. 60 times 60 will be 3,600. So we have 3,600 seconds. And if we do that calculation, we're going to find that our U, our potential energy stored, is actually 3.6 times 10 to the 6 joules. Okay? This is just a sort of straight multiplication of the two of these, and a watt second is a joule. Okay? So this is sort of intermediate step that we need here, but we want to find what the L, or the self-inductance needed in a coil would be to be able to store this much potential energy if it had a current of 200 amps running through it, right? Well, we know from above that we can write U is equal to 1/2 Li squared, right? And we can rearrange this to solve for L, and if we do that, we already know I and we know U, so we're basically there, right? If we solve for L, we're going to end up with 2U over I squared. And now we just have to substitute in these numbers. This U is going to go in here, and our 200 amps is going to go in the basement. So we're going to end up with an L equal to 2 times 3.6 to the, or no, 3.6 times 10 to the 6 over 200 squared. Okay. If you do that calculation, you're going to find a self-inductance of 180 henries. And so, while 180 henries is a large self-inductance, it is a value that we can build presently today. It's not always cost-effective, and if we think back to the previous video, this is much larger than the self-inductance for the coil that we looked at in the last video. So this is a pretty large self-inductance, but like I said earlier, it is doable, and it is a method that power grids sometimes use to store energy in low demand hours to be able to then supply that energy when demand is higher. Okay. Okay, so that's the only example for this video, and this is the second to last section that we're going to be doing in this chapter. So I'll just leave it here, and I'll see you guys in the next one.